Hello and welcome to AP Precalculus. Today, we're going to dive into the world of logarithmic expressions. Our main goal in this lesson is to learn how to evaluate logarithmic expressions. By the end of this video, you will be able to take a logarithmic expression and find its exact value without a calculator, or understand when you need to use technology. At its core, a logarithm is simply the inverse of an exponential expression. It's a way of asking a specific question about powers. So, if you're comfortable with exponents, you're in a great starting position. Let's start with the most important concept, the definition of a logarithm. A logarithm asks the question, to what power must we raise a specific base to get another number? We read this as log base b of c equals a. It's asking, what power do we raise the base b to in order to get the value c? The answer is a. This is the core relationship you must understand. A key strategy for evaluating logs is to always rewrite the logarithmic statement in its equivalent exponential form. So, log base b of c equals a is the same exact statement as b to the power of a equals c. They are just two different ways of writing the same mathematical relationship. This transformation from logarithmic to exponential form will be our primary tool for solving these problems. Just like division by zero is undefined, logarithms also have certain restrictions on their parts. It's crucial to check these restrictions carefully. There are two main rules to remember for a logarithm to be defined. First, the base, b, must be a positive number. In other words, b must be greater than 0. We cannot have a 0 or a negative base for a logarithm. So, for example, log base -2 of 16 is not allowed. The base must be positive. Second, the base b cannot be 1. Why? Because 1 raised to any power is always 1. A logarithm asks, to what power do we raise 1 to get c? And unless c is also 1, there's no unique answer. Therefore, log base 1 of any number is not defined. Always check your base to ensure it's positive and not equal to 1. Now, let's look at a special type of logarithm, the common logarithm. When no base is explicitly written for a logarithm, it is assumed to be base 10. This is a common mathematical convention. For instance, if you see log 5, it's automatically understood to mean log base 10 of 5. The number 10 is a very convenient base, especially in science and engineering. For example, a single unit increase in a base 10 scale represents a tenfold or multiplicative change. Think about powers of 10. 10 to the 0 is 1, 10 to the first is 10, 10 to the second is 100. Each step is 10 times the last. This multiplicative change is a key feature of all logarithmic scales. We'll see this in action later in scales like pH and the Richter scale. Now, let's put it all together and evaluate some logarithmic expressions. Remember our strategy, rewrite in exponential form. Let's find the value of log base 2 of 8. First, let's set the expression equal to some unknown variable. Let's call it x. So, log base 2 of 8 equals x. Next, we rewrite this in exponential form using our rule. The base is 2, the power is x, and the result is 8. So, the equation becomes 2 to the power of x equals 8. Now we ask ourselves, to what power must we raise 2 to get 8? We can rewrite 8 as a power of 2. We know that 8 is 2 times 2 times 2, which is 2 cubed. So, 2 to the x equals 2 to the 3. Because the bases are the same, the exponents must be equal. This means x must be 3. Therefore, the value of log base 2 of 8 is 3. Let's try another one that might look a little more challenging. It uses a fraction, but the process is exactly the same. Let's evaluate log base 5 of 1/25. First step, let's set it equal to our unknown variable, x. Second step, rewrite this logarithmic statement in exponential form. The base is 5, the power is x, and the result is 1/25. So we have 5 to the power of x equals 1/25. Now we need to find the power. We know that 25 is 5 squared. A fraction with 25 in the denominator is 1/5 squared. So we can write 5 to the x equals 1/5 squared. Recall from your exponent rules that 1 over a number raised to a power is the same as the number raised to a negative power. So 1/5 squared is the same as 5 to the power of -2. This gives us a new equation. Our equation is now 5 to the x equals 5 to the -2. Since the bases are the same, the exponents must be equal. Therefore, x equals -2. And so, log base 5 of 1/25 is -2. Let's explore two special cases involving the number 1 and the base itself. First, what is log base 7 of 1? Let's call this x. In exponential form, this is 7 to the power of x equals 1. Think about your exponent rules. Any positive number raised to the power of 0 is 1. So, 7 to the x equals 7 to the 0. This means x must be 0. We can generalize this. The logarithm of 1 with any valid base is always 0. Now for our second special case. Log base 4 of 4. Again, let's call it y. In exponential form, we have 4 to the power of y equals 4. To what power must we raise 4 to get 4? That's simply the power of 1. So 4 to the y equals 4 to the 1, which means y is 1. Generally, the logarithm of the base itself is always 1. So far, we've only seen examples where the logarithm evaluates to a nice, neat integer. What happens when it doesn't? Let's consider log base 2 of 5. Again, we set it equal to x. In exponential form, this is 2 to the power of x equals 5. Now, can you think of an integer exponent that works here? 2 to the first is 2, and 2 to the second is 4, and 2 to the third is 8. Since 5 is between 4 and 8, we know our answer. X must be between 2 and 3. There is no exact integer or simple fraction that will solve this. This is where estimation and technology come in. For logarithms that don't have an exact integer value, you'll need to use a calculator. Using a calculator, you'd find that log base 2 of 5 is approximately 2.3219. The key takeaway here is to recognize when an exact solution is possible and when it's not. Let's pause for a moment to recap the core ideas we've covered for evaluating logarithms. First and most importantly, always rewrite the logarithmic statement in its exponential form to solve. This is the golden rule of logarithms. Second, check the base. Remember, it must be positive and cannot be 1. If it doesn't meet these criteria, the logarithm is undefined. Third, and this is a great mental shortcut, always ask yourself, to what power do I raise the base to get the number inside the log? If you can answer that question, you've found the logarithm. And finally, if you don't see a base, remember that it's the common logarithm, meaning the base is 10. You'll need to memorize this convention. Beyond just calculation, logarithms are powerful tools for representing vast ranges of numbers. This is why they are often used to create logarithmic scales. Logarithmic scales are used when we have data that varies over many orders of magnitude. A key feature is that each unit increase on a logarithmic scale represents a multiplicative change, not an additive one. A 1-unit jump on the scale means the quantity you're measuring has been multiplied by the base of the logarithm. For a base 10 logarithmic scale, a 1-point increase means the measured value is 10 times larger. A 2-point increase means it's 10 times 10, or 100 times larger. You see these scales everywhere in science. The pH scale, which measures the acidity of a solution, is a base 10 logarithmic scale. The Richter scale, which measures earthquake magnitude, is also a base 10 scale. And sound intensity, measured in decibels. All of them use the principle of multiplicative change. So, while our main objective today was evaluation, it's helpful to have this broader context. Logarithms are not just abstract math. They are essential for understanding the real world. Let's quickly summarize what we've learned today. Our learning objective was to evaluate logarithmic expressions. We accomplished this by understanding that a logarithm is just a power, or an exponent, that answers the question, to what power? We saw how to convert any logarithmic statement into its exponential equivalent. The definition, log base b of c equals a, and its exponential twin, b to the power of a equals c, are the keys to evaluation. We learned to check the base restrictions and to assume base 10 when none is written. We practiced evaluating several examples, including special cases, and one that required a calculator for approximation. You are now equipped with the fundamental skills to evaluate logarithmic expressions. Keep practicing these concepts as they form the foundation for all the more advanced logarithm work we'll do in the future. Thank you for watching.